Here we go, boys and girls. This is assignment 4G worksheet. This is day number 2 of related rates. Again, what related rates are is we're in essence going to be taking a derivative with respect to time. So if you take a derivative of something like a v or an r, yeah, you take the derivative, but you have to attach like a dv dt or a dr dt, which is the rate of volume or rate of radius or whatever the case may be. Okay, here we go. A spherical snowball is being made so that its volume is increasing at a rate of 8 cubic feet per minute. At what rate is the diameter increasing when the diameter is 12 meters? Okay, I always like drawing pictures even if they're not necessary. All right, so here's our sphere. What do we know about this sphere? We know that its volume, so its volume is increasing. So that is at 8 cubic feet per minute. I think this is supposed to be a foot, not a meter. I'll make a change. So there is that, and then what is the rate of the diameter increasing when the diameter is, we'll say that's 12 feet. So the diameter is 12 feet. All right, now I noticed that the volume formula doesn't use diameter. So it's worthwhile to note that a diameter is 2 radiuses. All right, 2 radiuses, which is being used. So if I have a diameter of 12, that also implies that my radius is equal to 6. Just put that out there. All right, so yeah, let's go to work. Yeah. All right, so volume is equal to 4/3 pi r cubed. All right, so the derivative is dv dt. Derivative over here is on the r, so that 3 comes multiplied with 4/3, so that's just 4 pi r squared. And then I took a derivative of r dr dt. And the question, what is this question asking? At what rate is the diameter increasing? Shoot, okay, all right. Let's stop up, back up. Like, this equation has nothing to do with diameter. So what I'm going to do is I am going to make it a diameter. So r is equal to 1/2 diameter. Now I can play with the diameter. So volume is equal to 4/3 pi r, which is now 1/2 diameter to the third. So the volume is 4/3 pi. This is 1/8 diameter to the third. And so 4 and 8 simplify to a 1 and a 2. So this is going to be volume is equal to 1/6 pi diameter to the third. Okay, now I'm in the world of diameters, and because what the question is asking for, ultimately what I'm asked to figure out is what is the dv dt, like what is the change in diameter with the change in time. That's ultimately what the question is asking. So here we go. dv dt is equal to 1/2 pi, excuse me, as you were. So multiply by 3. I should have specified what I was doing. So multiply by 3, so that is going to be 1/2 pi diameter squared dt. Could have maybe chose a different letter, but whatever. And I want to know dt. I can plug and chug from here, or I can manipulate this just a little bit. So this would be a multiply by a 2, divide by pi, and divide by diameter squared. You don't have to do that. I typically usually don't do this. I usually just kind of plug and chug and do a little bit of algebra. I don't usually solve it completely out and then put in the numbers. I usually plug my numbers into there and solve however I need to solve. But I can do it this way too. All right. So this is 2 times the dV divided by diameter squared. So that's 12 squared. So this is equal to 1/9 pi. I didn't involve the pi. And this is a diameter, so this is feet. Feet. Feet per time, which is minutes. Okay. Just to also give you kind of a heads up, this would be equivalent to 0.0354. Okay, sand is being dropped at a rate of 10 cubic meters, so volume is changing at a rate of 10 onto a conical pile. The height of the pile is always twice the base radius, so the height is always 2 times the base radius. At what rate is the height increasing? The height increasing when the pile is 8 meters high. Okay. So this is a cone. This is a cone. All right, so volume is equal to 1/3 pi r squared h. And again, I don't want to deal, if I can so help it, I don't want to deal with an r and an h. And notice that all of the questions are asking for h. So I want to save all the h's and get rid of all r's. And so what I'm saying to you is this. In this equation right here, I have the ability to solve for r. So r is equal to 1/2 h. So what that does for me is this. I can rewrite my main equation with r being 1/2 h. Now, the only variable besides volume that is in here is the height. I'm not dealing with a radius that I don't really have a whole lot of information about. I want to know stuff about h, so I make sure I have everything possible solved for h. Okay, the square is going to be a 1/4, so this is a 1/12 pi h to the third. All right, here we go, derivative time. So derivative with respect to time, multiply with that 3, so that's a 1/4, and then dH dt. I'm solving for dH dt, so what I can do is I start with dV dt, so I start with 10, I multiply by 4, and I divide by h squared, so I divide by 64. And then I also divide by pi, so my dH dt is going to be equal to 5/8 pi. 5/8 pi. The top is a height, which is meters. The denominator is time, which is minutes. So again, if I divide this by pi and get an actual number, this is the same thing as saying 0.1989. 1989 here. I may have done this differently in different videos. If you see it done in a different video, do it this way. This way is way incredibly easier. So a straight light is hung 15 feet above a straight horizontal path. Notice how that height doesn't change. Here's our path. A man 6 feet tall is walking, etc., etc., walking away from the light. So here's an X and here's Y. Y is the shadow. X is the guy walking. And so the X is increasing. So the only thing that is really changing in this is dx, and that is at 5 feet per second. Okay, how fast is the shadow lengthening? And so the shadow is very specifically y, not x and y, but just y itself. Okay, that is the shadow. All right, so we have two similar triangles. The similar triangles are this little triangle and this big triangle. Those are my similar triangles. And so what I'm going to do is I'm going to set up ratios of similar triangles, and we will figure out, the question is how fast is the length of the shadow changing, and that's, again, very specifically dy dt. All right, so let's set up the big triangle. So the side is to its base is equal to the little triangle. The side is to its base. Okay, the side to the base is the side to the base. Okay, again, this is way easier than how I show in a different video, if you do see it done in a different video. All right, cross multiply, so that's 15y is equal to 6x plus 6y. Subtract 6y, so 9y is equal to 6x. Time for a derivative, so 9 dy dx is equal to 6 dx, excuse me, dy dt, I'm sorry, 9, it's changing with time. Dy dt is equal to 6x dx dt. And again, the shadow is the y. So that's 6 times 5. 6 times 5 divided by 9. The top is a y, that's a length, so that's feet. The dt is a time, which is seconds. And so then that's 3.3. A water tank is in the form of an inverted cone. Is being emptied at a rate. So the volume is changing at a rate of, it's being emptied, so it's the volume is decreasing at 6 meters cubed per minute. The altitude is 24 meters. I call that height. The altitude of this cone is 24 meters, and its radius is 12 meters. How fast is the water level lowering when the water is 10 meters deep? Okay, I'll talk about all of that here in just a second. All right, so what we have in this cone is a water level. So there's water in this cone. All right, and so what I'm going to do is I notice that the height of this cone altogether is 24, and its radius is 12. Okay, and then there's this water level on here. So I'm going to create that, and then there's this water level from the mid over. So this is a 12 and this is a 24. And then compare that to the water level that has a height and a radius. All right, so I know that 12 is to R, as 24 is to H. Okay, now the ultimate question is, how fast is the water level lowering? So again, H is the height of the water. So the ultimate question is, what is dH dt? So if I take the volume of the water, don't think of the cone, think of the water. The volume of the water is 1/3 base pi r squared times height. Okay, that's the volume, again, of the water. And so what ultimately is the question asking for? It's asking for things that are related with H. So I want to keep all the H's and get rid of all the R's. So if this is 12H is equal to 24R, R is equal to 1/2 H. So 1/4, ultimately making this 1/8. Excuse me. So what again I did is I eliminated the R's and I wrote this formula in version of an H. Okay, and so what else do I have? I want to know it when the height of the water is very specifically 10. Okay, if the question was asking for radius stuff, I would do the exact same process, but I would do it backwards. I would say, you know, H is equal to 2R, and then I would, you know, take out the H and write everything in version of an R if the question were asking me about radius stuff. But it's not asking about radius stuff. It's asking about height stuff. So I want to talk about heights. All right, here we go. dV dt is equal to, so the H to the third is going to be 1 second. Oh, I don't know why this turned into a 1/2. I'm like, this doesn't usually work out this way. I'm sorry. That's a 1/3. For some reason, I wrote it as 1/2. So 1/4 is a 1/12. That's the formula. Okay. So now multiplying with a 3 makes this a 1/4. All right. Ultimately solving this for dH dt, so I start with the dV, which is -6. I multiply 4. I divide by h squared. And I also divide by pi. So dH dt is equal to -6/25 pi on bottom. 6/25 pi on bottom. Double checking my answer here. Yeah. And so the top is height, which is in meters. So that's dH over dt. T is time, which is minutes. So divide this dude by pi. And so that would be -0.0764. Boyle's law for expansion of gas is PV is equal to C, where P is the pounds, square pounds per unit of gas. V is the volume. C is a constant, so C is a constant. All right, remember that. At a certain instant, the pressure is 3,000. So the pressure, when pressure straight up is equal to 3,000, the volume is 5 feet cubed, and the volume is increasing. The volume is increasing at a rate of 3 feet per minute. Find the rate of change of the pressure. So what's dP dt is the question. All right, so PV is equal to C, where C is a constant. So the derivative of this is the product rule. So this is derivative of p, so that's dp dt dv plus p, take the derivative of v, dv dt, is equal to the derivative of a constant, which is 0. So again, the question is asking for was dp dt. So I'll solve the p dv dt. So that's 3,000 times the dv3. So that has to get subtracted across. So that's a negative 9,000, and then I divide out the v, which is 5, and that's negative 1,800. Okay, the top is pressure, P, pressure, and so that's pounds per cubic, or excuse me, square foot. And the bottom is dt, which is time, and this is in minutes. Again, where I'm getting this label, I don't know if I really explained myself, is the top is pressure and the bottom is time. So pressure and time. That's exactly where I'm getting my labels. The stone is dropped into a still pond. Concentric circular ripples spread out of the radius of the distributed region. It increases at a rate of, okay, so the radius of the region increases. So the radius is increasing at a rate of 16 centimeters per second. What does the rate, at what rate does the area, so at what rate does the area of the disturbed region increase when the radius is 4 centimeters? Area is equal to pi r squared. So dA dt is equal to the radius, so that's 2 pi r, so that's the derivative dr dt. The question is the area, so this one is just straightforward. 2 times radius times the changing radius. Is 128 pi. The area is centimeters squared. The time is seconds. Times pi. One, 2, 3, 9. That's the ball game.